Hey everyone, and welcome to the first ever EMC FastPass YouTube video. And where better to start than one of the most fundamental concepts in EMC, and that's the current loop. So in this video, we'll be diving into what current loops are, why they're important for keeping radiated and conducted emissions down, and we'll be doing a few experiments as well to investigate the concept. So let's just get stuck in.
Okay, so current loops, what are we talking about here? Let's start from the basics and just take a battery and a resistor. We'll connect them up with a wire and a switch. And as we all know from Ohm's law, the current I equals just the voltage divided by the resistance. So in this case, the current is 5 volts divided by 50 ohms, which equals 100 milliamps. Now, it's easy for us to see in this case that the current just flows in a loop. There's a flow of positive charges that flows out of the battery towards the resistor and passes through the resistor and returns back to the negative end of the battery. The return path, we could say, is just the wire that connects from the bottom side of the resistor to the negative side of the battery. But you can see that there's nothing special about this wire. It's exactly the same as the wire on the other side. So some call it a return path, some call the wires send and receive, but really they're just part of the same overall current loop. Now, if we imagine that we connected the battery to earth instead of the positive end and cut the connection back to the negative end of the battery, so what happens to the current in this case? Does it flow to earth? Well, of course, we don't get any current flow at all because there's no complete loop. The positive end of the battery goes to the same potential as the connection, and the negative terminal floats to minus 5 volts. So we can see that for the current to flow, there needs to be a complete electrical loop. And this is essentially what Kirchhoff's current law says, that the sum of all currents flowing into and out of a node is 0 in a closed system. Now let's take this a step further and take the same simple circuit, place it on a circuit board. Instead of the battery, we have a simple 3-pin low dropout regulator. It has a 5-volt output and a 0-volt or ground pin. And here's the resistor on the right-hand side. So we'll connect up the output of the regulator to the resistor and the other side of the resistor back to the 0-volt pin on the regulator. And by the way, I know this is super basic, but bear with me here, please, because we have to lay the foundation for beginners too. But again, it's pretty easy to see that the current's going to flow in a loop on the top layer here on this circuit board. You can think of the send current flowing out here and the receive current flowing back here. But in reality, it's just one loop. Now, what if we put the receive track down on a different layer? Well, let's drop a couple of vias and put a track on layer 2. So where does the current flow now? Yep, of course it flows through the vias and back on the track on the back side of the circuit board. And what if we had a ground plane on layer 2 instead of a track? Well, in this case, we can see that the send current travels out on the track on the top layer and the return current flows down to the ground plane and back up through the via to the regulator. The ground plane just performs the same function as a track. It allows the current to flow back to its source through a very low impedance connection. So at DC at least, it's pretty easy to visualize how the send and receive current flows in a loop. Now, is it the same if the DC current is replaced by a switching current? Let's take a look. Let's put a load at the upper left here and a driver IC at the lower right. And there's a ground reference on layer 2 of this circuit board for return currents to flow. And by the way, this simulation example was taken from a paper by Dr. Marco Klingler of the Peugeot Citroën car company. And it was presented at the 2009 EMC symposium. It's a really good paper. I recommend you look it up online and check it out. So let's see what the current distribution in the ground plane looks like for very low frequency switching currents. Well, at 10 Hertz, barely above DC, there's a hot spot at the source and the load, and it's spread out kind of evenly in between those two nodes. But if we up the frequency to 100 Hertz, it looks kind of the same, maybe a little bit of change there. But if we go up to 1 kilohertz, the return current is basically directly underneath the send conductor now. It's spread out a little bit, but you can definitely see that the current is flowing beneath the track. So if we crank up the frequency again to 10 kilohertz, now the return current is much more tightly positioned below the track. It isn't spreading out as much on the ground plane as it is at 1 kilohertz. And then if we up it again to 100 kilohertz, it does look much the same as at 10 kilohertz. But if the simulations were in a higher resolution, I'm pretty confident that what you'd see is that the current distribution would be even tighter beneath the track than at 10 kilohertz. So what we can take from this is that currents concentrate under the tracks as the frequency increases. But why does that happen? Why would the return current flow more tightly beneath the conductor as the frequency increases? And the answer to this lies in the definition of impedance. So let's explore that concept in more detail. And that's the concept that current always takes the path of least impedance. And as a result of that, at DC and low frequency, say for example under 100 kilohertz or thereabouts, currents take the path of least resistance, and at high frequency, say above approximately 100 kilohertz, current prefers to take the path of least inductance. And as an example, the impedance Z of an ideal resistor is purely real, and we refer to it as resistive impedance R. And if inductors and capacitors were ideal, that is, if they didn't have any parasitic resistance, capacitance, or inductance, then they would have a purely imaginary reactive impedance. And the impedance of an ideal inductor, ZL, is given by J omega L. And the impedance of an ideal capacitor, ZC, is given by 1 over J omega C, where omega equals 2 pi times the frequency. And here's what all three of these look like in the frequency domain. The impedance of an ideal resistor remains flat across all frequencies. The ideal inductor impedance looks like this, which is to say that the impedance continues to increase with the frequency. And the ideal capacitor impedance looks like this, where the impedance decreases to 0 at a specific frequency. But in reality, due to the parasitics, here's the actual frequency response of each of these components. Here's what they might look like in a kind of simplified approximation. For the resistor, there's a dip in the impedance at frequency, then an increase as the parasitic inductance begins to dominate. For the inductor, there's a peak impedance which tails off as the frequency increases. And finally, for the capacitor, the impedance decreases to a point which is where the capacitive and inductive reactances cancel out, leaving only the equivalent series resistance of the component. Then as the frequency increases beyond that point, the parasitic inductance again begins to dominate and the impedance rises. So in the example simulations we just looked at, what we're seeing is that the current is flowing using the minimum amount of energy possible. And luckily for us, the path that the current naturally takes is the path that minimizes the amount of energy contained within the electric and magnetic fields. And in an analogy that Keith Armstrong uses, he's another EMC instructor, he compares this behavior to a water droplet in air, and it always assumes a spherical shape. and that's nature's way of minimizing the energy in the surface tension on the water. So at low frequencies, the least amount of energy is used if the current flows the path of least resistance, and at high frequencies, the least amount of energy is used if the current flows the path of least inductance. And that's a really, really important concept in EMI control. Now, how could we accidentally create an antenna on our circuit boards or systems? Well, let's take a look at two very common types of antenna, the loop antenna and the dipole antenna. And here's an equation that describes how to calculate a very rough approximation of the electric field intensity E at distance r from a loop antenna measured in volts per meter. We also see the equation on the right of how to work out the amplitude of the electric field due to a dipole antenna of length L when it's excited by a signal of a particular frequency and current. And what these two equations allow us to do is to quantify the amplitude of the electric field at, say, 3 meters or 10 meters due to two different types of antenna structures. So in theory, you could plug in the numbers and work out whether a particular track or cable was likely to break the far field emissions limits set by the FCC or other regulatory bodies. Now, interestingly, these antenna models are associated with different types of current on our circuit board. Loop antennas, for example, are synonymous with differential mode currents because differential mode currents are, by definition, they form a loop. And I'm sure we'll get into this a lot more in future videos, but differential mode currents are the currents that we normally see for switching, regular CMOS switching, for example, or power supply circuits. They're the currents that we actually want to generate and use for our own purposes. Our circuits wouldn't function without them. Dipole antennas, on the other hand, are more synonymous with common mode currents. And they're the currents that we don't typically want to occur in our circuits or systems. Common mode currents on external cabling is one of the most common sources of emissions failure mechanisms at an EMC test lab. I just wanted to give you a heads up that these two different types of antennas can be associated with the two different types of current that we'll need to think about when we're trying to control radiated and conducted emissions. But check out these two equations, and what do you notice about the attenuation factor at the beginning of each equation? And also, what about the frequency? Well, the most striking thing to me is the exponents in each equation. That's the 10 to the minus 16 or 10 to the minus 7, and also the f squared term. These factors lead to a situation where the amplitude of emissions caused by common mode currents tends to dominate below about a gigahertz. And as the frequency term gets larger, the f squared term in the loop antenna equation begins to become dominant. And what that means is that at higher frequencies, such as above a gigahertz, differential mode currents tend to be the main cause of emissions failures. And as an example, an excitation frequency of, say, 100 megahertz with a common mode current in the order of microamps, that's likely to cause more trouble in terms of emissions than a differential mode current in the order of milliamps at the same frequency of 100 megahertz. So that's what these equations point to. Now, above a gigahertz, the f squared term becomes dominant and differential mode currents tend to be our enemy. And this isn't set in stone though, so we can't make a blanket statement that only common mode currents can cause failures below a gig and differential mode currents cause failures above a gig. This just tends to be the way it is in most cases. Alright, so now we know about current loops, how they behave at high frequency, and why they cause radiated emissions. So it sounds like time for some experiments to me.
Alright, demo time. So what we have here is a clock source from IDT, that's this board. And if I connect up a scope probe here, We can see on the scope that in the time domain it's a clock and it's set to 25 megahertz. Now there is some overshoot and undershoot which is likely a result of the impedance mismatch from the load plus also the current loop that I've intentionally put in this circuit, which we're gonna be looking at. But also the scope has a 200 megahertz analog bandwidth, so we're not seeing a fully accurate representation of the rising and falling edges. The data sheet for this clock source says it should be in the region of 1 to 2 nanoseconds rise time, and that means the scope is going to slightly round off the edges a little bit, but it shouldn't matter for the purposes of this experiment. And the clock feeds into a circuit board that has various sizes of current loops intentionally placed into the return path. This board is an EMC demonstration board I got from the University of Twente in the Netherlands, so thank you to Professor Frank Lefrink for making these available. We're going to be using just the top loop here, and we'll be feeding in the clock source to the input, and there's a 50 ohm load on the output here. So if we take a near field probe and have a look at the high frequency content of this clock source, what we can see is that not only the 25 megahertz fundamental frequency is visible, but also the harmonics that extend way up into the hundreds of megahertz. Now, if you remember back to those horrible Laplace transforms you learned about at university, we actually need the harmonics, or some of them at least, to accurately recreate a square wave, or more correctly, in this case, a trapezoidal wave, since the rising and falling edges take a finite amount of time. For EMI control, often what we can do is to low-pass filter signals to attenuate the upper frequency harmonics, and the amount we can do this depends on how fast a rise time you actually need to maintain signal integrity at the receiving end. But we're not doing that here, we're just working with an unfiltered square wave, and you can see the harmonics extending up in frequency. Another interesting thing we can see here is that if I put the probe above the send signal, we can clearly see the signal. And in the receive path, we can see the current flow around the large cut in the ground plane. So the return current is attempting to flow directly beneath the send path, but because there's a cut, it's mostly flowing around the cut in a large loop. So we've artificially increased the area of the current loop, which means we'll have increased the amount of radiated emissions. And even worse, if you had multiple signals crossing this cut, they would all share this return path, and that would give you increased crosstalk between the signals. So this is a big no-no. You want to avoid this situation at all costs. Now, on this board, we also have a couple of buttons that connect to the ground plane. It connects the ground plane much closer to the send path, and it allows the current to flow much closer to where it really wants to flow. And remember, that's the path that inherently uses the least energy. So if I press the button, you'll see that the harmonics around the large cut drop off significantly, because the current can now take a much more efficient route. I'll just do that again another couple of times. So you can see those harmonics drop off quite a lot. Now if we look at the same thing on my EMSCAN unit here, unfortunately these aren't available anymore. EMSCAN was acquired last year. But I managed to snag one up. This is the EHX83 8 gigahertz model. Super useful for troubleshooting and also as an educational tool, because you can visualize where current is flowing and that kind of thing. But what we're going to do here is just sweep from 10 megahertz, 10, 15 megahertz up to around 200 megahertz and see how the current is flowing on the circuit board. And I'm not pressing these two buttons, so the current is actually flowing, the return current is predominantly flowing around the cut in the return path there. So let's kick off a scan and see how that current is flowing on this circuit board. Now this is super interesting because you can definitely see a hot spot, which is where the current is flowing around that cut there. So this definitely shows that predominantly the return path is going around this cut. And as we discussed earlier, if the current flows around the cut in the return path, it's bad news for a few reasons. It increases crosstalk, as I mentioned. It usually degrades signal integrity for the signal that crosses the cut because the return path experiences an impedance discontinuity. And from a compliance perspective, it increases the amplitude of radiated and conducted emissions. Okay, now we're going to run this again, and I'm just going to press these two buttons, which essentially shorts the ground plane on both sides of this, so it's bypassing, predominantly bypassing the loop that we created. One is a short, the other one is capacitively coupled, so it's essentially two connections from either side, which allows the return current to flow on a much more direct path. So let's have a look at what that looks like in the scan on the EMSCAN unit. So what I think you can see there is that the hotspot is no longer really there, at least not around the cut in the return path. It's much more tightly flowing below the track, and also the amplitude is lower as well. So yeah, by pressing the two buttons and joining the return path on the back side of the circuit board, we definitely improve the emissions performance of this unit. So let's just triple confirm that, and we'll take a look at a TEM cell as well, which allows us to take a look at the radiated emissions coming off this circuit board in the two configurations that we've been looking at. So what we have here is a TEM cell, and this gives you a pretty good idea of how your radiated emissions are going to perform. You can't really extrapolate to a far field measurement directly, but you can get a really good feel for relative measurements as you make changes to your circuit boards. So with the demo board in here, we can see the emissions from the board appear on the spectrum analyzer, and the interesting part of this experiment is what happens when I press the two buttons to shorten the return path. So I'll go ahead and do that right now. So lo and behold, the emissions come down by a significant amount. For some of the harmonics, 10 to 20 dB. So this little change can definitely mean the difference between passing or failing at an EMC test lab. And the emissions aren't perfect on this by any means. We do have an impedance mismatch on the load, and the short for the return path definitely isn't perfect, but it definitely does decrease the emissions when I press these two buttons. Alright, that's it for this episode. If you like these videos, let me know in the comments below. And if you want more in-depth training on EMC and EMI control, go to emcfastpass.com/products. There you'll find a number of online courses I've developed over the past few years. They're available to enroll and begin at any time. And yes, they're purely online, so you can get step-by-step EMC training wherever you are in the world, and with instructor support as well. So I'll leave some links below this video for some more resources, and also the link for connecting with me on LinkedIn is there. Finally, the more you like and share these videos, the more I'll know that it's worthwhile creating this content. So please do share with anyone you think is interested in EMC. But that's it for now. Cheers for now, and I'll catch you in the next video.